Here's another equation that describes a curve in the plane. We might like to find the slope of that curve, which we would call dy dx. But this is not a function, y explicitly defined as a function of x. I don't have y isolated on one side. And in fact, if you tried to do the algebra to isolate y, you'd break. You can't do it. Y can't be isolated. So if I want to find the derivative, if I want to find dy dx, I'm going to have to use implicit differentiation. So remember I said we're going to take the derivative of both sides of this equation with respect to x. So the easy part is right after the equal sign. Can you take the derivative of x squared with respect to x? Sure. It's 2x. That's the easy part. The other two pieces, the other two terms in my equation are functions of y. In order to take the derivative of a function of y with respect to x, we're going to take its derivative with respect to y, the variables that's there, and multiply by dy dx. That's one use, another application of the chain rule. So the derivative with respect to x of 2y, well, the derivative of 2y with respect to y is just 2, and then I'm going to multiply by dy dx. The derivative with respect to x of sine of y is going to be the derivative with respect to y of sine y, which is cosine y, multiplied by dy dx. So I have my next step. And notice I have not labeled this dy dx. If I had an isolated y and I took its derivative with respect to x, I would have dy dx. But what I have here is not that. It's different, right? So my new equation, I have 2 times dy dx is equal to 2x plus the cosine of y times dy dx. Remembering that dy dx is one single entity. It's not a fraction. It's not, the dy and the dx are two separate things. It's one symbol that means the slope of that curve. I want to isolate it. If I can isolate the dy dx, then I'll have an expression that can give me slope anywhere. And just remember, we saw this for the first time in that last example, my expression for dy dx might contain both x's and y's. So the goal there is to get any term with a dy dx onto one side of the equation, and anything that doesn't have a dy dx onto the other side. So I'm going to take that plus cosine y dy dx term that's on the right-hand side, I'm going to subtract it over. So my new equation now, 2 times dy dx minus the cosine of y times dy dx equals 2x. The way to isolate that dy dx is to factor it out. So you can see here, let's get a better color. The dy dx is common to this term and this term, so I factor it out. Now when I want to isolate dy dx, notice dy dx is being multiplied by the quantity, 2 minus cosine y. So in order to isolate dy dx, when the bell rings at 3 o'clock, I'm going to divide both sides by 2 minus cosine y. So I've isolated my dy dx, and notice again we have a slope that's a function both of x and of y. Okay, so just to summarize from those first two examples, if I want to find dy dx, but I do not have y as an explicit function of x, I can use this technique called implicit differentiation to still find dy dx. I'm going to take the derivative of both sides of my equation, so every term in the whole equation with respect to x, and then isolate the dy dx expression. Again, this is called implicit differentiation. It's taking the derivative when you do not have an explicit y as a function of x. All right, here's my next example. It's going to seem a little, it's like a couple notches up, but this is a very common kind of problem that you're going to see on the AP test. So we want to make sure we're ready for it. I have, again, it's not a function, but it's an equation that describes a relationship between x and y that I could graph. And I might very well be interested to find the tangent to that graph or find the normal line to that graph. So that's what this question is asking. I'm going to have to figure out dy dx to get the slope so that I can find the equation of the tangent line and then the equation of the normal line at this point, this ordered pair that I've been given. And you can notice they're not going to try to trick you on the AP test. If you actually use -1 for x and +2 for y, that's this ordered pair here that they gave you, that will work. That is a point on the curve. They won't give you a case where it's not a point on the curve. Okay, so here I am. I'm in this same position where I have this big crazy function that's got x's and y's in it, and I need to find dy dx. I'm going to take the derivative of both sides with respect to x. So let's look at the easy parts. The hard parts from before have now graduated to be the easy parts. I'm going to be able to take the derivative of x squared. No problem, that's 2x. And now this derivative of y squared, I'm kind of used to how this goes. So the derivative of y squared with respect to x is the derivative of y squared with respect to y times dy dx. So when I take the derivative of this section, I'm going to get 2y dy dx. The derivative of 7, that's a constant. Derivative 0, that part's easy. What part is here that's like new and kind of big and some extra work is now I have a product. So I'm going to have this case where I'm going to have to use the product rule with implicit differentiation. And all on top of that, I'm going to have this subtraction problem here, which means I'm going to have to remember to distribute the subtraction as I do this. Okay, so we're going to go nice and slow. I've written over here, the part of this work is going to be, the tricky part really, is going to be taking the derivative with respect to x of x times y. So this part you can probably follow along here. The derivative with respect to x of x squared is 2x. The derivative with respect to x of y squared is 2y dy dx. The derivative of 7 is 0. So here's the part where it gets interesting. Since you have this subtraction of a product, and we know we're going to have to use the product rule to take this derivative, I like to put this in big brackets just to keep it safe, to help me remember that at the end I'm going to have to distribute that subtraction. There are other ways to do it. This is what I do, so just make sure you pick something that works and you stick with it. So how do I take the derivative of two things multiplied together? I'm just going to come over here to remember. Well, this the first times the derivative of the second plus the second times the derivative of the first. But when I say that, I'm being a little loosey-goosey, right? I'm not specifying that I'm taking the derivative with respect to x of all of these. So the derivative with respect to x of x times y is x, that's first, times the derivative of the second. Well, the derivative of the second with respect to x, that's called dy dx. Plus the second is y times the derivative of the first. And to be specific, I'm taking the derivative of the first thing. The derivative of x with respect to x is just 1. So if I just focus on that x times y, when I take its derivative using the product rule, I'm going to get x dy dx plus y. And you can see that that's what's here inside these brackets, just to keep it safe, to make sure that I distribute that subtraction afterward. Okay, so now let's distribute the subtraction. My whole goal is to get the dy dx by itself, which means I'm going to need all the dy dx terms on one side and all the terms that don't have dy dx on the other side. All right, so I've distributed the subtraction. I've got the dy dx on one side. I'm trying to isolate dy dx, but it's being multiplied here by 2y minus x, so I'm going to divide both sides. Hopefully get some of the rest of this stuff out of your way so you can see. Okay, so here I have, I've isolated dy dx. It's equal to y minus 2x over 2y minus x. There's plenty of ways to rewrite that, which you can choose to do and choose not to do. Now that I have dy dx, I'm going to be able to use it to find the slope of the tangent line. Just notice, this is our first time, again, if you haven't already checked into your free response notebook, when it's going to be time for me to compute the slope at a point, and I'm going to need to know both the x and the y. But fortunately, I have that already. So dy dx is a function both of x and of y. I'm going to have to replace all the y's with 2, replace all the x's with -1, and I can compute a slope of 4/5. So I know an ordered pair on the line I want. I know the slope. I'm going to use point slope form to write the equation of this tangent line. And just notice that we have once I have the equation for the tangent line, I'm simply going to use the opposite reciprocal slope with the same ordered pair to write the equation of the normal line. Notice if you're taking the free response section of the test, you can feel totally free to leave your answer like this or like this. You're welcome also to change into slope-intercept form. They both get full credit.